Okay, so let me recap exactly what we're doing here. Again, one of the main goals of trigonometry, one of the great promises of trigonometry, is to be able to just look at something, and by measuring the angle, just by measuring this angle here, more or less, and measuring one of the sides, you can measure everything about this triangle. So, for example, just by looking at this tree, you could possibly figure out how tall the tree is. That's one of the great promises of trigonometry. Well, I always try to make it sound nicer or more fancier than it really is. You really just can't tell how big a tree is by looking at it. You really need to look at it, measure the angle, and know at least one side. Why? Because we had this discussion that it's all about the ratios. When you know the ratios on a triangle, all you need is one side. From one side, you get the other three sides. That's how the ratios fit together with the knowing how tall the tree is picture. Okay? I know I always say you just look at it and know how tall it is. The truth is that, I think now you're ready for the truth. The truth is that you look at it and you measure one of the sides, and the point is that often measuring this side here on the bottom is easier than measuring this one. Or sometimes it gets even fancier. You could, for example, just measure, for example, let me see, measure this angle right here. Just measure the angle here, theta, and you could maybe walk away here. I don't know, let's see if I can control copy, control paste, and then you come over here and you measure the angle again from farther away. And so the point, and you could measure, say, this distance and measure this angle, say I'll call this phi, and measure this distance, and then that would be another fancy way to measure the tree without ever being even close to it. So let me rephrase. You could just look at it, measure the angle, measure one of the sides, maybe this side over here, look at it again and measure that angle, and boom, you'll know exactly how tall the tree is. That's the great promise of trigonometry, to be able to do that. If you can do that, maybe someday you too will be the life of the party, and people will look at you and say, whoa, that guy has got magical powers, or that girl's got magical powers. Alright, so anyways, that trick, the heart of this problem, by the way, this is one of the essential problems of trigonometry, and the essential way to do this is, of course, this discussion about the ratios. Every time you know the ratios, all you need is one side, and you can figure out the other sides. That's why here you need at least one side. Anyways, it's all about the ratios, and so hopefully by now you can see the great importance of knowing the ratios on a triangle. If you know the ratios, hey, you're in good shape. That's the first part of it. Now, after that, we said, hey, you know what? We can actually figure out some ratios already. Here are some of the ratios that we know. We know for our 30-60 triangle, we know the ratios. For 45 triangle, we know the ratios. For an almost triangle, we know the ratios. So in every one of these cases, we're in good shape. As long as we know one of the sides, boom, we'll figure out the other two sides. And maybe someday be able to tell how the trees are by just looking at them. Now, the next step is we made the language a little bit fancier and a little bit more traditional. Instead of calling them ratios and ratios and ratios, what we do is we call them, another fancy word for it would be to say, you know what, you could replace this word with sine functions values, okay? So we could say this is the same thing as the sine or cosine, all the trig function values, okay? I'll just write trig values. That's the same thing as knowing the ratios. In fact, trig values are ratios. Okay, we've got all kinds of opposite hypotenuse, opposite adjacent, blah blah blah. 6 famous ones. Trig values, it's the same thing as ratios. So if we know already all the ratios for the 30, 60, 45, 45, then we also know the trig value for those for all the functions on those famous angles. And that's where we're at. We will interchange when I talk about we know the ratios. It's the same thing as knowing the trig values. When I talk about knowing the trig values, same thing as knowing the ratios. However, we come to a difficult problem. What happens when you have something other than a 30, 60, 45, 45, or an almost triangle? What if it's not one of those? What are you going to do now? Where are you going to run to? Are you going to be scared, running away? Ooh, I can't do it. Well, actually, you should, because it's actually much more challenging than one may think. And I try to think, back in the day when my hands were tiny, tiny, tiny little hands, how did people used to calculate these ratios for non-famous triangles? For example, suppose I've give you a triangle here, and this triangle this is a right triangle, this is 23 degrees. Whoa, how are you going to figure out the ratios? What is the ratio of the hypotenuse? If I'm staying from here, this side is called the opposite. I'll just call it O for opposite. Well, that looks like a 0. I'll just say OPP for opposite, and I'll call this the hypotenuse. No. What am I on? Adjacent. So from this point of view, here you are. This is the opposite, adjacent, hypotenuse. How do you know the ratios? Well, this right here is not that easy to know the ratios. In fact, historically, people would used to carry around tables, big old long tables that had a column that would say 23 degrees. It had all the degrees, and then on top it would have sine, cosine, tangent, and you would look at the 23 degree row and the sine column, and you would get that, and it'd have some approximation rounded to about 4 decimal spots. But that really doesn't answer the question. That's silly. Where do the tables come from? And you say, well, some guy printed them. Well, that doesn't answer it. Where did it really come from? How did people figure it out? And that, my friends, that's an interesting question. How would you figure out on a 23 67 right triangle? What is the ratio to go from the hypotenuse to the opposite? What do you have to multiply by, or to go from the hypotenuse to the adjacent? That's the question, and it's not it's not trivial. Let me give you some ideas on how you could possibly figure it out. Let's take it back a couple thousand years. Suppose you were a caveman or cavewoman in the time of the dinosaurs. And suppose back then, there's no calculators to figure this out, no computer, no Googling anything, and you just had to think with your noodles. All you had is something like this. Well, a nice lap. Maybe all you had was like rocks and sticks and stuff. But anyways, suppose back then you wanted to figure it out. What is the ratio on a 2367 triangle? Here's one silly approach. You could take first you would take a protractor. That's these things that measure degrees. They have little markings on them. Of course, those are just estimates, but you would try to estimate it as best as you could to make sure that's exactly 23 degrees with the protractor. And if there wasn't one available, you'd have to make one yourself. I have to make my own protractor. No worries. You could make your own protractor, and then you could do something silly like say, hey, if you want, I want another ratio, I'll just measure it. So once you draw a triangle, by the way, this was a big topic here during the time of the Greeks. How do you draw perpendicular to another line just using a ruler and a straight edge and a compass? This is a huge topic. I'm just gonna let that slide for now, because I got other business to take care of. Anyways, so you with whatever means you had, you would draw this perpendicular, you draw the triangle, you do your best you can, 23 degrees. Here's a silly way to do it. You would measure, hey, the hypotenuse is equal to 15, okay, and the opposite is equal to, well, you would just measure it and say, hey, that's about 7. So therefore, you could say, you know what, the ratio of opposite You put these two together and you say the ratio of opposite to hypotenuse is approximately 7/15. That would be a very, very crude and primitive way to try to estimate the ratio for 23 degrees. Again, let's keep focused. All right. The immediate task at hand is to be able to look at things and measure them just by looking at them, and maybe just measuring one of the sides. The key to that is the ratios. If you know the ratios on a triangle, one side is enough. From one side, you know the other three. You can figure out the other two. We already know some ratios. We already know the ones for 30/60. We already know the ones for 45/45. We know the ones for almost. To know the ratios is the same thing as knowing the trig values. Okay, these are exactly the same thing. Well, the trig values even go further. They give you negative ratios, and they go all over the XY plane on second, third, and fourth quadrant. But we use this interchangeably. When you know the ratios, you'll know the trig values for those angles. We knew the ones for 30/60, 45/45. Trying to figure out what the hell are we going to do with 23 degrees. We explained one silly way to do it would be to take a protractor and just measure this, measure that, boom. You get a rough estimate. But, of course, that shouldn't feel that good in your conscience. If you have a math conscience, that should feel like, all right, whatever. But that's for kids. Because, sorry, no offense to kids, but that's for very, very first level of understanding. It's for primitive way of understanding, because there's got to be a better way to estimate. You know, there's so many errors here. What if you didn't draw your protractor correctly, or what if you missed it by 1/100th? You know, if you're measuring things like the moon or the stars, that could amount to huge errors. So this leaves a lot to be desired. You'd like to do better than just measuring stuff like this. So then let me take you to the next chapter in history. This was the time of the dinosaurs. Of course, I'm just kidding, because humans were not there. So let me fast forward a few thousand years to the time of Newton and the post-calculus world. After calculus was discovered, there was this. Here's an incredible breakthrough. This idea that there's this bridge between two different worlds. This world of functions that don't appear to be polynomials, such as sine x, and this other world that is exactly polynomial, well, a very, very long one. I can tell you how it starts. It starts off with x minus x to the third over 3 factorial plus x to the 5 over 5 factorial minus, well, it keeps on going for a long time. Well, for a really, 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 really long time. I can't tell you everything because it goes on forever, but there's this bridge between the sine function, which is a ratio, and this polynomial. This one right here could be calculated by hand, and it could be calculated as precisely as you had time for. And so, using methods of Newton and calculus in the post-calculus world, we could in fact calculate these by hand, and people did that, and they wrote long tables that others could use. Of course, the real story behind this is way beyond the scope of this class. So you'll have to settle for something like, man, I can't wait to really, really learn how to calculate these ratios. Maybe in Calculus 2 you could do that. More than that, this method is not going to be accessible to our class because the ideas that are required for it are outside of the class. So that leads us nowhere. Well, it gives you a little historical perspective and something to look forward to, but for the present task, it's not the most helpful. So that brings us to let me think. So let's fast forward a little bit here. After Newton, not too long ago, some of you may remember these things called slide rules. What you would do is you had a bunch of markings on there, and you would move the markings to exactly the right spot. For example, this is 30/60. That would be a 30/60 triangle, and it would give you the right ratios. So this is analogous to the table, and you could just move this thing and calculate whatever you want to calculate. You could even flip this to the other side and you'd get, you know, conversion stuff if you want to convert yards to meters, whatever. That's the way people used to do it for a long time. But then let's fast forward. That still doesn't leave you, it still shouldn't leave you feeling very good about doing it, because you're really not understanding how to get it. You're just copying the work of somebody else. And in the bad news, sorry to tell you, is that for today and for this class, that's all we have. All we have is the very prideless method of just copying other people's work. In fact, to really understand how to compute this is outside the scope of our class, and it will remain so. So let's fast forward some more to the current time. This I shall call this the post Walmart era. Nowadays, you can go to any Walmart and pick up one of these calculators, and that's going to be the prideless way. Absolutely no pride. What you do is you figure out how to use it, make sure it's scientific so that it has the right buttons. It should have a sine and a cosine button. And the way we're going to do it is just like this. We will do sine, and then we will do let's see, we will do sine of 23 degrees, for example, and that should give us the approximate answer. Or here, let me put one on the screen for you. These calculators look more or less like this, and they all have this mode button where you can change from degrees to radians. And so suppose we're in degrees and we're trying to figure out 23. So you type in, I'm going to go with sine of 23. It already knows it's degrees, so I'll just hit the equal, and it tells me an approximate answer here. So this is saying that it's 0.39. So this is saying that sine of 23 degrees is approximately 0.39. That's great. We've got the ratios now, all thanks to the calculator. So now, if let's go back to our well, I'll come back to that. Let me finish this one. So before we go on, I want to make sure that everyone really understands exactly what this means. This means that on your triangle, on your right triangle, to go from the hypotenuse to the opposite, this is the opposite to the hypotenuse ratio. Now, this is telling you that the opposite is approximately 39% the size of the hypotenuse. Okay? Opposite is approximately 39% of the hypotenuse. That means if you wanted to go from the hypotenuse to the opposite, you would multiply by 0.39. Hope you can see that. Let me see if I can zoom you in there. Zoom. To go from the hypotenuse to the opposite, you multiply by the square by 0.39. This is multiply, not x. This is multiply. Of course, to go that way, you would divide by 0.39. To figure out the ratio this way, we would use the cosine. Cosine is the function that describes the ratio of adjacent to hypotenuse. So if I calculate cosine of 23 degrees, I get that that's approximate. Again, we'll use our little on-screen calculator. Let's see, I will push the cosine button. First I'll clear that. I push the cosine, 23, then I push equals, and it tells me 0.92 approximately. This is the ratio of adjacent to hypotenuse. What exactly does that mean? Well, that means that the adjacent is approximately 92% of the hypotenuse. So to go this way, you would multiply by 9, 2. That is, you multiply. Okay? Let me rephrase that. Let me redo that so that there's no doubt. So sine of 23 degrees, which is the ratio of opposite to hypotenuse, is approximately 0.39. That means to go this way from hypotenuse to opposite, you would multiply by 0.39. Obviously, to go backwards, you would divide. And cosine of 23 degrees is approximately 0.92. That means to go from the hypotenuse to the adjacent, you would multiply by 0.92. It's approximately 92% of the hypotenuse. Of course, to go backwards, you would divide. Clear? So every time you calculate this, every time you use a calculator and you get some decimal, you must have some deep understanding of exactly what that decimal is telling you. It's telling you the ratios, all the ratios. Not only, and of course 23 is just symbolic for all the non-famous ones. This stuff, the calculator will give you all the ratios for all possible angles, even fractions of an angle. I could type in cosine of 23.2757 degrees, and boom, the calculator will give me a really close approximation of it. It won't give me the exact because it doesn't have enough space for the digits, but it'll give me a very, very close approximation. And in doing so, that's the bad news. Unfortunately, we want here. Let me backtrack a second. So trig values are ratios. We knew the 30-60 ratio. We knew the 45-45. We knew the almost triangles. And now we will know all of them. Not really know how they're calculated, but we will know what they are by just typing them on the calculator. Okay, so all the rest of them, the non-famous ones, let's call them non-famous. All the non-famous, let me use non-famous angles. I gotta assume you guys are there. Sorry. Now, all the non-famous angles we will use, we will know the ratios by the calculator. Okay, I'll just use C for calculator. And with that being said, now the task is for you to, 1, practice using the calculator, practice switching from degrees to radians. Second, every single time you calculate anything, make sure you know and understand exactly what that's telling you. Okay, let me repeat that. Now the task is to practice using the calculator, practice calculating these ratios. Second of all, every single time you calculate it, know exactly what that calculator is telling you, what it means. Let's just do one more example like that to wrap things up. Suppose you've got a triangle here. Let's just say this triangle is funky little triangle. Let's say 37 degrees. Okay, and suppose you type in there on your calculator. Suppose you go, hey, I want to know what sine of 37 degrees is. So we go to our little calculator here, we clear everything, we go sine of 37 degrees is equal to 0.60. It's not equal to, it's approximately 0.60. Okay? Approximately 0.60. What in the world is that telling you? Okay, this is the important thing. Know how to calculate it, know how to use a calculator, and second, know how to interpret that. What does that mean? Well, that's by definition, that's the ratio of opposite to hypotenuse. From this corner, which one's the opposite and which one's the hypotenuse? This is the hypotenuse, this is the opposite, and this is telling you the ratio. It's telling you that the ratio is about 60%. So to go that way, all you would do is multiply by 60%. Of course, to go backwards, all you would do is divide by 60%. Okay? Let's calculate, let's do some other ones. Say tangent. Tangent of 37 degrees. What is that equal to? Well, let's use our little magic calculator. No pride. Have no clue why it's done that way. Just use a calculator. How does that make you feel? Tangent of 37 equals 75. Approximately 0.75. 0.75. What in the world does that mean? You must have a good idea of what that means. Well, the tangent is by definition the ratio of opposite to hypotenuse, right? No, just kidding. Opposite to adjacent. So what in the world does that mean? That means that the opposite is about 75% of the adjacent. So this is the adjacent. If you wanted to go that way, from opposite to adjacent, you would multiply by 75%. The opposite is 75% of the adjacent. Of course, if you wanted to go backwards, you would divide by 0.75. So for example, if you could plug in any numbers there. You multiply by 60%. To go this way, you would divide by 75%, and you get the adjacent. And I promised you, why are the ratios so important? Because every single time you know one side, the ratios will give you the other two. That's why they're so important. And of course, we already knew these other ratios, 30, 60, 45. Today, we're all about the non-famous angles, and the calculator, no pride way of finding the ratios. And again, this is where we left off. Ultimately, what we want to do is we want to be able